Yes. Yep.
Yep. Great. Well, thanks to those of you who came and kind of have endured the last two for the last part of this trilogy on essentially an extended example of GDS and what you can do with it. That's more or less what we're looking at. But we're trying to look at it from the what you can do with it from a formal setting. There's a lot of high, let's say, abstract applications that we're embedding into this and trying to ensure that an example that's being discussed renders some of these fairly abstract ideas relatively more tangible. That's kind of the way we're wrapping up today, is to say, well, all right, we're doing a lot of this, but we're an organization where people come and ask us, we have a problem, can you help us with this? And then we try to propose solutions. So this last bit is about not just representing a system, but also discussing its design and ultimately its controllability. I'm glad to hear it, David. Thanks. So just as a quick rehash, we have the crosswalk problem, the problem of this pedestrian who needs to cross the street. The location of where the crosswalk is a decision from some other governing body. We have traffic that is, in some sense, encapsulating the state of the system, but also is something that people may want to condition upon for what they desire for the traffic flow. And then there may be objectives, individual objectives for the people who want to cross. And what we're doing in this environment is taking that example and creating, in that first part, a representation as a generalized dynamical system. So we say, here's an explicit way to formalize this whole thing within the context of this, paying attention to this separation in a way between state transitions that are conditioned on decision-making on the one side and the decision-making that is taking place by individuals who are either inside the system as decision makers or outside of the system as exogenous shocks on the other. And we've explored then, as a result of this formalization, where it can fail, for example, potentially not go well, but also examine things like what we would expect to see as an outcome of the system left to its own devices, perhaps from an equilibrium point of view, where we look at strategic decision-making, or as saying conditional upon the fact that people can choose from this set of admissible actions something. What is it that we might see as the trajectory of things that could happen? What are the possible future universes? What's the multiverse that kind of like expands or spreads out from that admissible action set? And so today what we're going to do is sort of bring that back down and say, okay, well, it's great that we can see a multiverse out there, but really what we're talking about is designing something. We're thinking about this in the example context of placing the crosswalk in a certain location. So we want to figure out, how do we embed or in a way leverage the GDS framework within the engineering design space? And so what we'll treat now are the ways that we have, the levers that we have as designers to be able to take this GDS representation and then say something about what should be chosen, what should be done in that environment. And the bundle that we're going to use for that, which is the one that we typically use actually across a wide variety of projects, is the mechanism design part of this, which says under certain conditions have this type of arrangement, coupled with initial conditions. How does the system start? Where do we place the system so that when we turn the system on, it doesn't just fly off into something that causes us to have problems with the system as a whole, or it doesn't go to its expected outcome. And that's kind of the wrapping up of this. And we're also going to use, by this point, the example is we'll be starting to show some frayed edges. I'll kind of identify those as we go along. There are limitations to the level of dimension reduction, let's say, that we've done in this example, but it hopefully will serve well even to carry us just across the finish line, if not perhaps much further than that last goal. Okay, so the one slide example of what we've been looking at as the reduced form of this system has the state of the traffic flow, xt being the state of the environment. The pedestrian has various decisions, such as whether or not to cross, where they cross, and then there's this exogenous feeling of, are they lucky? Do they feel lucky today to cross the street? The decision making that we're going to focus on as part of the design process is the crosswalk's location, K. And given all of these factors, plus an exogenous representation of the probability of having an accident, just this epsilon that we use in that bottom row, we can generate the transition matrix from, on the first column side, the current state partitioned into three different groups, just for simplicity. So we have three different blobs of an accident environment where the xt is less than 0, xt being equal to 0 stop traffic, xt greater than 0 flowing traffic, and then the probabilities of moving from one state to the next. So this is kind of our super reductionist version of the world, given the way in which individuals can interact and then how the state changes over time. And this brings up the fact that we have this design decision. Explicitly, the notion of where to place the crosswalk is something that's being done by people who are examining the system and saying, okay, you've come to me now with a question, where do I put my crosswalk? Now let me look at the system and give an answer or a range of answers. Previously, we did a little bit of this. If you remember last time, we had some behavioral assumptions, especially for the equilibrium analysis, that restricted the selections from the admissible action set. So for example, a focal point or a Schelling equilibrium says, hey, people will condition on this if you condition on it. So sort of like a Nash equilibrium notion of what do we condition on as an equilibrium that would lead people to use a particular crosswalk location as a focal point. Well, that was nice because it gave us a prediction, but it was also something that had as its bedrock, let's say, the assumption of what people are doing if they are in fact conditioning upon these things in a focal point kind of way. And the observation then to lift up a bit away from behavioral restrictions ex ante is to say, okay, well, I've got the parameterization of the system with respect to K. K at least partially parameterizes that state transition, that Markov matrix, which we'll see once again. And so that transition matrix itself has the interpretation of representing an entire class of matrices, one for each K, that satisfy and rely upon the admissibility of the pedestrian's actions, because the S's and the L's and the P's are all feeding into that. So you can think of that entire matrix as a class with the undetermined value of what K is. Specifying one particular K is as if, and I'm using a loose analogy for object-oriented programming, selecting an instance from this class. And this class to instance paradigm is really something that pattern itself works really, really well for design, because you can actually have, based upon the way in which you are specifying mechanisms, classes that are functions, not just a parameter or a vector of parameters, but classes that are functions of functions. So you may have a continuous space of functions, all of those functions of which can be used to parameterize that particular mechanism that you have of interest. So mechanism design itself then says, hey, we've got requirements for this system. The system has to behave in a particular way. The laws of motion of the system are such that we can create a class that satisfies those requirements. That's the matrix, this transition matrix K, where K is left open. It can be anywhere along the road, but it's still a transition matrix. The instance from the class, though, is selected from something else that we add to this when we look at the system as a whole. And we say, well, we've got actually criteria that says some Ks are better or worse than others, depending upon the design criteria that we are putting forth as the objectives, as the point of designing the system. And just for the purposes of the way and stakeholder objectives are multitudinous and of course have many different dimensions, but for the purpose of this example, let's restrict the notion of a design criteria ultimately to what's being observed or being conditioned on for the state. So we would say design criteria select either or both of parts of the state that are desirable for state trajectories. We want the reachable states in the end to go to that particular point. And what might be seen sort of as a converse, we want to avoid perhaps other parts of the state space which are bad. So for example, the one we'll be leading for the rest of today, the idea of being in a state or an absorbing state where people continually just walk across the street and get hit by cars is just an area we would like to avoid. We may not be so concerned if the only alternative is to spend most of your time in a traffic jam. That may still be preferable to being in a situation where you're always in an accident, even if you would really like the best design criteria fulfillment would be in the environment of always having traffic flowing. So we use this design criteria to choose that specific value for X. And parameter selection, whether it's under a system which is completely closed with no exogenous shocks, or like this one, which has luck coming in with uncertainty from the outside. So parameter selection under uncertainty, being the term we have adopted for the most general specification, is the process of selecting the instance from the class that meets the design criteria, or at least gets as close as possible to meeting the design criteria as we ourselves can create thresholds for. Now, that's part of the story, and that's actually a large part of the story when we describe most of the systems, when we do things like the preliminary and the conceptual math specifications prior to a CAD/CAD implementation. A lot of the mechanism design is that particular point, pulling out the instance or at least representing the class such that CAD/CAD can do instance, can actually select the instance. But for those of you who've worked with CAD/CAD, you know you also have to start the simulation somewhere. And just a question from Chris, talking about selection, referring to the design process only, or do you also mean the ongoing governance of the system afterwards? In this case, the initial design recommendation according to the design criteria is selection from our point of view, the point of view of the designers of the system. But of course, the design criteria can evolve over time. And once the system is live, the governance process may also end up selecting a different parameter value for that K, given different constraints. If, for example, a crosswalk is in a particular location, but they know that that location is going to be changed, or that part of the street's going to be, under construction for several years, maybe they need to move it to a different location, changes the design criteria, changes the selection. So anything that impacts ultimately in our particular case, that value of K is part of that selection process. Okay. But thinking now about CAD/CAD and the idea that, well, you can start the simulation and let it run with the different mechanisms and select the different parameters that are part of that simulation process. Well, what you're doing is you're ending up selecting the specific from the general. And what you want to be able to do, as you know, anytime you run a CAD/CAD simulation, is start it from something. In order to really pin down particular design criteria fulfillment, you often require a combination of both the instance itself that you're selecting and the initial conditions that you start from. This is often overlooked, or sometimes you would like it to be the case that you're totally independent of initial conditions. And this is where we're going to start seeing the frayed edges of this particular example. But it's important to note that if you can't start the system in such a way that you get to the design consideration that you want, then what you've done in essence is you've lost the ability to actually set the system up to fulfill the instance that you've selected. So controllability is part and parcel of the design space selection process. And so the formal definition of this is you are selecting the initial conditions such that the instance of a dynamical system that you've created generates the trajectories that satisfy the design criteria. And that's controllability. There's no big brother control. It's not meant to be any kind of qualitative features of puppet mastering, not at all. It's really the system has to start from something. You have a degree of freedom in some cases on where the system starts from. And so being able to show, either analytically or through simulations, that the combination of the instance that you've created for the mechanism and the mechanism design, coupled with the initial conditions that you've created, can lead to satisfaction of the design criteria, completes the picture. And then you could say, here you go, these are the parameter recommendations or the range recommendations plus a series, perhaps a range of initial conditions. We think that you could actually, to the client, this is what you could use for your design process. What we're going to do now is build up the things that people typically need to have as understandings of the system. Let's call these refinements of the existing dynamical system to be able to start talking about things like controllability. So what we'll do now is build up very slowly in our crosswalk example, well, relatively slowly, and the understanding of what is it that the system sort of does on its own. And then at the end, we're going to layer onto this a design characteristic to say, what would we choose among the options, this continuum that we actually have of the location for the crosswalk. Okay, any questions before we move on further? Okay, so what we would like to do is to concentrate on this transition matrix to understand its impact that it itself has, the laws of motion itself, on what we think may happen next. And because it's a transition matrix from 3 different states in 3 different subsets in the state space to those same 3 subsets later on, a natural way to think about this would be to say, well, what if I were to walk over to this particular corner or to this street and just watch things that happen and generate an empirical distribution? What is it that the system itself is telling me about the relative frequency of one or another of these subsets? Because if one is much more common than another, or if one is an absorbing state, then we can be sure that the reachable states after some period of time collect in that subset. And so we're thinking about the overall probability distribution for the different subsets of an accident, traffic jam or traffic stopped, and flowing traffic. And that means we have essentially from a Markov process, this transition matrix is a stochastic matrix, which I'm now going to be labeling as M. It's the same one that you've now seen several times, but we are now going to be treating this as something that allows us to move probability mass in and probability mass out. So we're looking at really this formalization of what the Markov process itself is. The simplest thing to start with, at least conceptually, is the idea of what happens if I put in a particular probability distribution of being in one of these three states. I apply this transition matrix, and what comes out is the same thing. That means, of course, if I put it back in again, it comes out again at the same thing. It's a fixed point of the mapping, the linear mapping M. Stationary probabilities are defined this way. And here we have left multiplication on the right-hand side just because of the way that the Markov matrix is written. But this pi star is this idea that the system itself may perhaps converge to this invariant of the system. And that's important because if it's the case that you, number one, identify stationary probabilities, and then number two, can show that they are converging to those probabilities, well, then you're able to say under what conditions, if this is true for every K, for example, you're able to say, well, crosswalk location doesn't matter. The coordination of the system is so strong that we don't have to worry about this. If, however, you can parameterize the stationary probabilities by K and generate a relationship between K and the stationary probabilities, well, that tells you something about this design criteria that comes later. So it is important just to understand what happens to the system under the different conditions that could occur before deciding on embarking on how to select it. And so that's this idea of looking at the Markov matrix is really writing down what's happening as you're standing on the corner to kind of intuit these different relationships, that data-driven analysis that we know is critical to be able to understand a system, and then examine these different stationary probabilities for the different decisions that the pedestrian makes in different crosswalk locations to tease out these regularities. So what we're actually doing is very simple, well, relatively simple. We're taking this Markov matrix, and then we're randomizing. We're just randomly drawing whether or not a pedestrian will cross, where they cross, how lucky the pedestrian is, and where the crosswalk is placed. So we're just doing this every period as if there was a universe in which we actually draw the pedestrian randomly, and then we have the crosswalk fixed randomly at the beginning of a trial, and then we're looking for backing out the stationary probability as if M was the same. We're going to change M every period in a little bit later, but for the stationary probability, it's that Markov matrix is fixed for one time, for one period. And these fixed values then, the things that are coming from outside the system that we're not randomizing over are the exogenous accident change, which we may assume is some kind of a actuarial data, for example, the probability of an accident that just happens, and then the length of the street. We're just going to say that the street's going to be the same length, probability of an accident ex ante without a pedestrian, it's always going to have some baseline value. And the result of this, which I'll show you in just a moment, is that the stationary probabilities themselves appear to be independent of the crosswalk location. In other words, we don't gain power from understanding where we place the crosswalk, but it does depend fairly trivially upon the crossing decision, which may or may not seem intuitively clear. But let me quickly switch my screen over to the Jupyter notebook that kind of goes through this quick thing to show you a visualization that is hopefully going to be quite useful. If I can find it. I can't find it. Oh, I see. So Zoom ate it. All right, hang on. Here we go. Okay. So this is just a very simple notebook. I'll post this in the channel after I've had a chance to document it more thoroughly so you guys can play with it. Just random draws of things like luck, the crossing locations, whether or not to cross, and setting a few ex ante values for example, the ex ante probability of an accident, saying 1% perhaps, and the length of the crosswalk for various values. And then we go through and calculate the stationary probabilities. Those come out of the eigenvalues and the eigenvectors for the linear system that we have. I also compute, just as a sanity check, some limit probabilities. We're going to leverage those a little bit later. But in the end, what you end up with then is some existence of, for each one of these combinations, some probability mass that when you act on that probability mass with M, gives you back that mass once again. And if you look at the plot of this, for all of the different types of trials over all of these different randomizations, very simple uniform draws we're using here. What you end up with is one long line, which gives you a regularity on the entire system, which has the probability of being in a traffic jam or the probability of an accident being non-zero. That's everything down here. But the probability of the traffic flowing being exactly zero. So you reach an absorbing state, a stationary probability, which always has the probability of having flowing traffic being exactly equal to zero. And then you have this little guy up here, which seems to say, well, hey, there's this crosswalk location of 1/2, and there's a probability of actually having fully flowing traffic. Now, this is actually duplicitous. In fact, what's happening here is that there's actually many points overlapping each other. And we can tease that out by changing the color that we see on this graph. Instead of looking at the crosswalk location, this value between -1/2 and 1/2, and using instead the crossing decision, whether or not the individual crosses the street. And if you do so, same data, but different coloration, you can see that anytime anybody crosses the street, traffic stops. The guy doesn't cross the street, traffic just keeps moving. And that's a feature of this transition matrix M. So not a lot that can be gained except for an understanding of the fact that we get this split in what is essentially a higher level projection of the state space to our three various locations that we are concerned of interest. But really over a variety of different values for K, we don't get any kind of regularity that exists. There's nothing here that we can pull out and say, this is the way we can depend upon that value of the crosswalk, the location, for this particular type of envisioned long-range movement. So stationary probabilities are a useful feature, and some more complex versions or other versions of the transition matrix may tease out very interesting regularities. In our particular case, not so much.
Would you see a variation once you introduced more complex, either behavioral or exogenous processes representing say the distribution of preferences of points to cross? Like if for whatever reason let's say that there's a bar on one side and a park on the other side or something, and like the very fact of the businesses that are there might lead to a high concentration in preferences for crossing, and particularly low values of luck if we're talking about drunk people. I'm just like kind of playing with the concepts to ask, like, when would something more substantial arise, and like what new assumptions would you have to make before that started to pop out?
Yeah, I think those are really good points, and all of them are indeed along the lines of refining ways in which we would be pulling out these draws of the decision whether or not to cross and the crossing location. So the more, and we're going to see just a little bit of a hint of this in just a minute, in fact, but to jump ahead and sort of give a sneak peek, exactly as you're saying, if you can actually create a behavioral model or a model in which you are looking at different outcomes with a probability distribution and then explain where that distribution perhaps came from, or even just from testing a parametric
Before
system.
you move on, though, I would make the point that this is a bit like an ordinary differential equation without a forcing function, right? It's kind of banal with no input. But once you say, here's the one that doesn't have a driving function and its behavior is rather banal, but I understand what it is, then you can start asking how that system processes a signal from outside. And in this case, that could be a driving function that's just sort of totally exogenous, or something that's endogenous and state dependent. But ultimately, it's not until you attach that other piece that you actually start to see the real mechanics of the system. It's sort of hiding in the simplicity of the solution when there's no driver.
Yeah, that's a nice point. I think it's good to make sure that when we use the word driver, of course, we do think about things like actually forcing the system, but we can also generalize that to the notion of having something like, for example, Fourier analysis or a Fourier transform, where we have a whole mishmash of different forcing frequencies that come out to approximate a particular functional form. But that's exactly, I think, the way in which we're going to lead sort of to our end limit of this example. We're going to kind of just barely start to graze that. But I think that's a nice way of saying, here's where you would go next. Yeah. Okay, I'll jump back into the presentation, then we'll jump back into the notebook in just a moment for one last bit. But that's essentially the result of this initial foray, is this notion that, well, we can definitely see something, but at the same time, we're getting something and understanding really of the regularities that are associated with the system before we start designing. Now, the stationary probabilities are interesting in their own right because they are, in essence, a facet of the transition matrix, but it doesn't really lead to a great deal of realism, because you're actually saying the same individual is coming over and over and over and over again, doing exactly the same thing, and then we're just watching what happens for that transition probability to converge. So we would, in fact, like to have something which is more about a path, perhaps to a stationary probability, perhaps not, but one which actually allows us to infer that there are many different people that show up one after the other. So we actually generalize a little bit and say, well, we know more people than just one show up, and we know that they change or even the same person changes their mind from day to day on whether or not to cross and where to cross. So let's actually start from a particular initial condition and then see what happens when we apply this M matrix, the state transitions, for different realizations of individuals' decision-making. So we're numerically simulating the different pedestrian decisions, by the way, not the behaviors, because we're still randomly drawing, but we're getting closer and closer to what Zargham is showing, is that sort of that idea of introducing the outcome as from behavior as a forcing function. And it requires randomizing over now the thing which was causing us to give the idea of whether or not somebody crosses or whether or not they're lucky. So now we actually start lifting the level of the randomization to say, well, we're going to randomize over the probability of being lucky, because different people carry different kinds of luck. We're going to randomize over the probability of crossing. So in essence, we're saying not that everybody has an identical distribution over the crossing decision, that people have different distributions that are part of their characteristics, even if we don't know what they are. So we select some number of pedestrians that may or may not converge to a limiting probability over these state subsets: accident, traffic jam, or traffic flow. Here we're going to use 50. 50 is more than enough. We end up usually getting to a limit convergence somewhere around 20 or 30, 30 being that economist's magic number for everything converges and it's all beautiful. And then we're creating 3 different initial conditions, because what we want to be able to say is, well, it's coming from a particular starting point that we want to see what happens to the system. And now we're defining explicitly the starting point. And we choose, in this particular case, 3 degenerate probability distributions. One, which states that traffic is flowing for sure. That's 0, 0, 1, coding in the value of the probability mass being entirely on traffic flowing. The second one being stopped for sure, 0, 1, 0. And the final one being in an accident for sure, although you may not want to necessarily choose that one as your initial condition. You do want to test and see what happens if that initial condition is perhaps constrained or something else has happened. And that's 1, 0, 0. And the result of this, which I'll show you in a moment, is again this notion that the limiting probabilities appear to be independent of the initial conditions and the crosswalk location. But we are going to see some very loose, I put that in quotations, dependence on the crossing decision itself, even though the crossing decision, remember, is changing with each of these M applications of the power. So we glean a little bit more information. We're getting a little bit closer to the idea of what might we expect to see in this system if we then start to think about designing it. And so here then becomes this is the code then for just building out an initial condition. You start from a diagonal matrix, because that's the matrix which, when you multiply, gives you the same thing back, and then essentially create a power of this M function for movements of probabilities of crossing and where the crossing location is. And notice that for each one of the trials that you're doing, you're choosing one and only one crosswalk location. So there's no changing every period of the crosswalk location. It's fixed at the beginning, and then you run the trial. So we can start looking then from the initial conditions What is it that we see? And the initial conditions themselves turn out to be independent in the sense that the system goes to the same locations in this representation of the probabilities, independent of the initial condition of starting in an accident, in a traffic jam, or with flowing traffic. So I'll just show you the one particular representation. All three of them look the same. Here we're choosing as the initial condition the accident. So this is where we're selecting out of all the runs that specific value. And again, looking at the crosswalk location doesn't tell us very much. The crosswalk location varies all the way across the board. We do see, however, a separation, again, of the space into two pieces. And here the separation is richer than we had before. We again have an entire number of locations for which we see that probability of flowing traffic being driven to zero. But now we have actually a line of separation for traffic flowing across different regularities. And we can see there's a regularity here because they are all dimension reductions to a line. So we're seeing a trade-off there. And of course, that's by design, that's coming out of the way that the matrix probabilities have lined up. But it's leading us to this question of, well, hey, what if I code it again for the crossing decision? Maybe these are all up here, these are all red for not crossing, and these are all back to the crossing locations. And you see here that the limiting probabilities are richer. So if we color for the crossing decision, where 1 means the individual crossed the street and red, and 0 means they did not cross the street, you see a mixture. And so we're no longer able to say that the state separates according to the crossing decision. But what we do see is that maybe there's some feeling of, hey, if you don't cross the street, you get good traffic flow. And maybe there is some correlation here that we could perhaps tease out between crossing and maybe what the value is from up here, oops, for the value of the crosswalk location, perhaps. But this is part of the data-driven analysis. You're actually able to see that there is this partition in the state space, and then teasing out why this is occurring becomes one of the queries before you start looking at the full design, or while you're actually applying different design characteristics for the crosswalk location. Okay. So we've got stationary probabilities, which are sort of inherent in this particular understanding of a transition matrix, but is fairly unrealistic behavior where we're cloning an individual and sending them across the street each period. We have limit probabilities, which say, given an initial condition, people arrive, and conditional upon where the crosswalk is once and for all, they do stuff. And then we just kind of see the probabilities converge over time. And what is interesting, and perhaps from one point of view, slightly remarkable, is the fact that there are limiting probabilities. So for every one of these initial conditions that we randomize over, if you run them 50 times, even though every time people are choosing whether or not to cross and choosing where to cross randomly, you still arrive at limit probabilities. So there's still a driving function within, driving force rather, not driving function, but driving force within the M matrix itself, which shows that you end up with different limiting probabilities over time.
So I want to make a tie in here, though. This means that the structure of the model is actually processing the signal. So like in the sense that you have this random, this distribution from which you're drawing the inputs to this, and then the structure of the road and the traffic and the crosswalk ultimately represent a kind of filter that takes in the what I'll say, it takes in the signal in the space of the that you're sampling from, and outputs something like a signal which represents the distribution that the limiting distribution. And so we can start to interpret this as saying it will take this distribution to that one. And that's actually really important, because when we're designing, we pretty much never know what the inputs, the random processes or strategic processes are going to be, but we can say something potentially about how our quote system transforms one distribution or one signal with certain characteristics to another signal with different characteristics. And it's not quite the same to talk about temporal signals versus sort of the spatial quote signal in terms of the probability distributions, but there's a lot of rich I guess like techniques that you can use to sort of understand the spatio-temporal relationships between, here's what is happening, and here is how the infrastructure or the apparatus converts that input into output. For lack of a better language, I'm just trying to emphasize that it's not something where you can assess the outputs without some assumptions about the inputs, but you can still assess the transformer or the transformations that are produced between some a priori unknown sequences of activity and the properties of the distributions that the sort of output from this particular mechanism. I don't know that there's a better way. I mean, Jamsheed, do you have a sense of what the right vernacular is for describing these sort of input output operations as having properties independent of the knowledge of the input distributions or input processes?
I think transform is probably the best way to view this. And in fact, we're going to see in that example for the design problem that transformation process acknowledgement is unavoidable. And so I'm trying to think of whether or not I've heard of any kind of a term being adopted for, I've chosen this input probability distribution and what comes out as another probability distribution through a transformation, other than calling it a transform. Because so much of that is being done in a Fourier series environment or coded for a Fourier series environment, I would say
that makes sense. I mean, for everyone's reference, I think of it as a block, which is actually what the company's named after. And so, it's sort of funny to see it again popping up and trying to figure out how to place the right name on it, because the hardest thing about this work is that you cannot actually assert any properties about what will happen truly. You can only assert properties about relationships between input and output. So at the end of the day, what you're designing is the block or set of blocks, or the transform or the set of transforms that are induced by the system that you're deploying, not an actual behavior. It's just that because it processes or filters or steers behavior, it's still going to have potentially meaningful properties in terms of, for any valid input signals, you will get output signals that are within some reachable sets, trajectories within these reachable spaces. And it's part of the reason why there's so much emphasis on reachability here, is that it characterizes the set of what can happen, but there's also this slightly more nuanced thing, which is, the processing or filtering that occurs, which is to say how signals on the input side actually get mapped into signals in the configuration space.
Yeah. Yeah, I think that's an important distinction, because the visualization, for example, confounds both of those. It allows us to make the powerful conclusion that there are whole areas of that probability distribution combinations that ex ante we have thought maybe anything could happen. And we find no, that not anything can happen. Everything is really on two lines. We've actually reduced the entire state space's possible probabilities to those particular lines in three space. But of course, they're probability distributions. And so as long as there's mass in one or another one of those sets, the reachable trajectories themselves are going to hop between those different sets. And so then as a way, kind of taking your remarks and then moving to the next step forward, just to ensure that that's something that people should think about. The next, what do you do after that? Looking at things like ergodicity and, how much time do you spend in one or another of these sets, then becomes the next analog up for reachability. And that may end up being, for very complex systems, you may not be able to claim that it stays within one set all of the time, but you may say that a large part of the mass, more than just the probability mass, but some other metric that's being used to capture the amount of time that it spends inside this. Of course, you can tie those together formally with ergodicity, but if you don't have an ergodic theorem to help you, that separation may be quite useful from an analytical point of view. All right. Okay, so that's kind of our structural analysis part of this, where we're kind of getting ready to do the design aspects. And a lot of the work that we do in that preliminary math spec, where we're just teasing out how do domains and ranges map to each other, what's allowed, what can happen, how might these things be affected by what we put into the system, and what comes out, is in that context. Now let's move down to what we can, as far as we can, in this limited example, to the idea of actually choosing something, designing something such that we end up in an environment which has fulfilled some criteria. And so here, let's take as our example for the crosswalk problem, a design criterion to minimize the probability of an accident when an unlucky pedestrian crosses the street. So we're just going to have the person who just, they were at Zargham's bar before they came out, they're crossing the street, they're weaving across. And we want to make sure that regardless, they can still maybe make a choice on where the crosswalk is. Maybe they see 3 or 4 crosswalks, we don't know. But they're crossing the street conditional on being unlucky and making the decision to cross. And so what we want to do is, of course, to find a way to make transitions to the accident subset in the state space to be rare, or even if ideally never. And we can look at pulling out just that transition that we see from the Markov matrix. And so I'll jump back to that very quickly here. If you notice here, that first column of the M matrix is the column that says, regardless of where you start in the 3 rows, that first column is where you end up as probability of an accident happening. And so here you can see that the salient term that is adding probability mass to getting into an accident is this term that starts with S and ends with 1 minus L. And so if you say now, and this gets back to the idea of the forcing function or the forcing input, that there exists some distribution of where people cross. And we don't know anything necessarily about where people cross. We'll say there's some distribution across the road of where people cross. Then we can create an expectation of this probability mass that contributes to an accident. And notice now that it actually has its own defined, let's say, value where we've removed the uncertainty of the individual in terms of where they choose to cross. And because we're conditioning upon them deciding to cross, S is equal to 1, and that they're unlucky, that L is equal to 0, we've removed any other dependencies on things that are not being conditioned on for expectations, except for the design decision of the crosswalk location K. And the thing that's coming from the outside is this decision maker's estimate of the probability density function of the pedestrian's crossing location, F of P. And I guarantee you every regional, in every regional decision-making body in all of the local and regional governments has a series of probabilities on distributions of where individuals cross versus what they don't cross. Data comes from the police on jaywalking and so on. There's a lot of data that you can think about or even decide on how you would collect yourself for figuring out what that F might look like. Or again, parameterizing the F function for a variety of different parameters and then figuring this out. But the goal here, and this is why this functional form was chosen, is to minimize the probability contribution, minimize this value with respect to K, because that then meets the design criteria.
I want to note that there's a partial observability problem there that like also shows up even in the stronger cases, like our on-chain observations. You pretty much never know about when someone decides not to do something. So like here, you might make really good observations about where people had chosen to cross, but you'd have probably very weak observations about the circumstances under which someone just didn't cross because they didn't cross the road at all. It'd be like someone coming up and considering a blockchain transaction and then not doing it. Like insofar as that those concepts have to exist or do exist within our models, they're always going to be inferred.
Yeah, that's true. And in fact, here we've even got this set up deliberately so that the conditioning that is happening is that the individual is crossing, so that S is equal to 1. If S was equal to 0 in our very, very simple model, if they choose not to cross, then it doesn't matter where the crosswalk is. And of course, in a more complicated environment, that's not true. So I think it's a good point to highlight the limit of the example to say partial observability really makes a difference if you want to include that mass.
It also is particularly important if what you're building either induces the likelihood, increases or decreases the likelihood of choosing to cross. So if you minimize you could actually minimize the probability that someone unlucky gets in an accident, but you might actually inadvertently create more accidents by virtue of inducing more people to choose to cross. So there's other competing metrics that live in the same world. And the point is not to do this analysis. The point is to highlight the inherent subjectivity of the framing choice. It's a valuable framing. It tells us something, but there's a adjacent framing that will give us a different perspective on the same system, even with this simple model. So like Jamsheed could simply, reorganize this to look at the probability of the count of accidents where we had a different distribution over the likelihood that someone chose to cross. Again, harder to measure, but the moment you introduce that, you're going to get a different result. And so it's a sort of a conflicting, potentially conclusion that you would reach from a policy design space. So when we're thinking about this algorithmic policy making, doing these successive simplifications to make it tractable is really important because it literally allows you to achieve conclusions, but the conclusions that you achieve are not, you know, they're no larger than the set of assumptions you made. So it's like a if, then. You might have to have a different if, other if, then. And so you start actually painting a picture around these systems when you do these analyses, where you're kind of honing in on different perspectives. Doing a single analysis where you sort of make successive simplifying assumptions until you get a result is often results in sort of like let's just say overfit solutions. And I don't want to derail you. That's a matter of like engineering practice that I think often gets overlooked in the economic literature, which will teach you to, reduce the problem until you have a tractable solution, but not necessarily to reduce the same problem 3 to 5 different ways to try to find different angles on the same problem.
I mean, I think that's completely valid. I think it's adjacent to, and in fact, I would be cautious a little bit to people who are still trying to disentangle the idea of behavioral assumptions versus what is admissible, to ensure that things like tying the likelihood of someone choosing to cross the street on the basis of a design decision, that has an impact on how the behavior of the individual is being modeled. And so I completely agree that you want to be able to throw in these different representations of the effect of a decision on somebody's future decision, but in that mapping is the behavior. And so you can't have that particular causality unless you are doing essentially an estimation problem and trying to back out conditional upon my different design decisions and observed distribution of outcomes that happen because of this, if you had the freedom to see such an environment. So I completely agree, but there is a little bit of a caution there that ability to make that dot connected can sometimes be, and very elusively be, a behavioral assumption that is snuck in the meantime.
Yeah. I think that's actually the point I'm trying to make, is that even though we're talking about structure, we've already entered the behavioral side of this discussion the moment we start making distribution assumptions, even though it's a stepping stone between them. So there's like pure structure and like things that are like, oh, the reachable space is only this. Nothing else can happen. Then there's these sort of probabilistic results that are more like, okay, if we make really relatively weak assumptions about, they're almost like sensitivity analyses where we're conditioning away a bunch of dimensions and seeing like, okay, like what's the sort of there's like a local probabilistic partial derivative like thing going on here in order to understand the sensitivity in a specific dimension to a specific part of the design. And then there's like moving towards a more holistic view as you go into like broader behavioral models that represent either scenarios or extreme cases or whatnot, to try to get a better understanding about holistically how things might evolve. But if I'm thinking about this practically, I'm going to go from structure to these sort of local partial derivative like analyses up to these sort of holistic, scenario, therefore trajectory type analyses.
Yeah, I completely agree. That's exactly the trajectory that ensures that the cart's never being put in front of the horse, essentially. And so this example kind of limits us in the sense of, well, we've limited ourselves to ensure that we're looking really at a structural interpretation. And here what we're introducing is not so much a behavioral assumption over pedestrians, but the observability power or technology available to the decision maker. And that's what's crafting this particular function F. But I think it's a good point to make sure that particular chain of events is respected, because oftentimes the client will wish to be at the very end of all of that and assume that that's what you start with. And then of course you're in trouble. Great to actually, those are really, really good points to ensure we know where the limitations are of these types of things and where we go from there, because there's never a blocker. It's just a question of how we generalize. To wrap up this particular example, to minimize this particular probability contribution, conditional upon the observed density of individuals crossing the street, we can leverage the fact that this is actually an expectation, an expected value of this distance from the crossing decision to the crosswalk location. And turns out this happens to be minimized by the median of the probability distribution. So that's that particular point K star, where the probability masses of being less or greater than K star are greater than or equal to 1/2. At that point where they're both, these things are satisfied, you can have more than one median, as we'll see in just a moment, then the chance of an accident is minimized when the crosswalk is placed there. And this only has to do with, well, only, quote unquote, only has to rely upon the fact that you can at least create some observation of what individuals are actually doing without knowing what it is that they are actually deciding or how the process has gone from choosing from an admissible set to that particular action. And to wrap all of that up, once you've actually specified the mechanism K star, controllability then is starting the initial condition from a desired point. And so if you start from an initial condition that's either a traffic jam, maybe from requirements or traffic flowing, then at least it isn't starting it from an accident. You would then want to see how the system moves from that point forward. Okay, so let's have a look, just a very quick stylized examples in the time that we have on what this would look like. Let's take a very easy example where people are crossing the street and you observe that they cross in this distribution. So we see a lot of gamers who are going to the gaming store all the time, and some people just don't care about crossing at one location directly across. We see some distribution that's symmetric. And so we could say, well, the median then location will provide us with a crosswalk at that point. Now, since this is a median, it's not unique. So we could, for example, have a different distribution of individuals all on the sides. So they're all at the areas where there are intersections with other streets, for example. In this case, any of the points in between is a median, splitting the probability mass exactly by half. And so you have to then think about what other design criteria are going to be placed on top of this. We have the minimization of an accident, placing it anywhere along this line, but there may be other things that we consider, like one of them is potentially better than another, or we want to induce individuals to move from one intersection location to another. We get this refinement of the design criterion as a result. And this happens a lot with client projects where we end up with an outcome of a particular type of recommendation. And then there's a refinement on thinking, okay, we need a new metric, we need a new measurement, or we hope that we have another measurement that will help us refine this even further.
This is a natural consequence of trying to avoid overcomplicating models, though, because you get a model that is the simplest one that allows you to understand the phenomena in question. And if that yields a family of solutions or a set of solutions that are agnostic to something that you actually do need to care about, the refinement generally means either extending the GDS structural model to include the new concept, or like enriching the model of behavior in order to create differentiation within what would have otherwise been a level set.
Yeah, that's very true. And that's kind of where I think a lot of the engagement, once you have set the expectations of the stakeholder properly, let's say, if that's a lot easier to come back to. And witness our initial discussions with the RAI team at the beginning, where they were very, very resistant to the notion of other criteria even being discussed, apart from making the whole system as valuable as possible from the point of view of their secondary market, all the way over to the end, where we really were raising other types of more nuanced criteria that they were under, they understood that those acceptances were actually moving the project forward. That also helped a lot to help clarify. Okay. So we kind of reached the end of this very simple example. This is really kind of extending to the point that we can kind of sort of get to the area where we're saying, okay, we have this nice environment of the median as a solution to minimizing the probability of an accident. That's our design criterion. It's worth emphasizing we've made no behavioral assumptions about pedestrian decision-making. We've used a data-driven analysis, but we had to add something. We had to add something to the structure of the system itself so that we could use the outcomes that could be observed from estimation to determine the optimal location of the crosswalk. And then coupled with the proper initial condition, the idea is, and again, maybe relying on ergodicity or maybe relying on CAD/CAD simulations, that the time spent in the desired location of the state space, i.e. the complement of the set of subset of no accidents, is maximized. And so in the paper that Zargham and I are just finishing up, we have some restricted conditions on when local controllability, that is controllability within a particular region of the state space for any GDS, is possible. Now there are restrictive conditions, and so there's a lot of research directions that can be taken to hopefully move us up that ladder to find greater and greater applicability. But for the most part, the computational complexity alone to guarantee controllability itself is typically more expensive than actually examining the simulation output from parameter selection under uncertainty, for example, with CAD, and then discerning things that meet the actual design criteria as encoded as metrics.
Yeah, and I might go so far as to say that like local controllability is a nice concept for differentiating one's ability to influence part of the system that is appropriate versus trying to control the whole system. So like, I know it's a sort of abstract and hard to discuss in words, but like there's something that you almost gain from relaxing and not trying to have, by not trying to have global controllability, but having something that's sort of weaker in the sense that it's defined locally. I think you actually make it possible to come up with results for things that might otherwise, I guess, steer you or bias you towards systems that are, I'm going to abuse the term, but like more centralized versus more decentralized, if they can be made coherent through local controllability rather than having to design for some sort of like global controllability. I know it's a little bit tough in English, but Jamsheed, I don't know if you want to comment.
Yeah, no, that's kind of what I was alluding to with this idea that you may be able to try to move heaven and earth to try and get global conditions even analytically. But at the end of the day, it doesn't empower you very much if what you could do is sample the state space sufficiently so that you actually find what you're looking for, which is just one set of reachable states or a range of parameter values that meets the design criteria. So I agree. The local controllability is important only insofar as you can, and this is again work in progress, define a basin of attraction so that like a marble rolling down into a small bowl, once it has reached the lip of the bowl, you know it's going to get there. But that's as far as we can go with local controllability. And so I think that distinction to ensure we don't over-engineer, let's say, to a global solution is avoided. Yeah.
But it does also mean that, kind of going to our governance work, it might be the case that that's a moving target and that like there's going to be circumstances in the future where you want a different solution, and that as long as there's some parameterization or sort of, some of those design decisions are actually parametric in nature and can be changed in the future. There's a lot of power in relaxing away from there's one global solution forever to there's a sort of co-fitness. There's many possible solutions that are co-fit with behavior, and that we just need to be, we need to find one that has a decent basin of attraction. And if it starts to shrink its basin of attraction, or if it starts to drift, that you have some way of understanding that, well, actually the design itself, the mechanism design might actually be able to drift with it to stay in sync.
Yeah, that's a good point, because it is worth emphasizing that we're really looking at this from the design criterion point of view. And so if at some point the design criteria that you started with has either been augmented or other pieces have been dropped, that's going to change, in fact, with the acceptability of particular choices to have been made from the parameterizations. Yeah. With regard to the question, Chris, I'm not sure I understand what you mean by initial observation. Do you want to kind of flesh out your query on, do you mean the initial observations of things that are being conditioned on, or the idea of controllability with an initial condition? Chris, are you there? I might have stepped out. Oh yeah, okay, very good. Let me go ahead and quickly give you the overall conclusion while Chris is away. Just to give you the overview of where we are, we've come full circle to controllability at the end all. We've walked through an extended example. So thank you for your patience over this time period of really what is, for the most part, work in progress continually as we keep trying to kind of pin down the things that are useful to kind of expand outward to the broader audience. We've represented the system as a GDS. We've described equilibrium concepts and reachability in state trajectories. We described controllability and mechanism design given design criteria. And we built the system to fail. It's an extensible example, but it's also a fragile example. And it kind of shows the assumption boundaries. And I urge you, if you have the interest and the time and the inclination to kind of bend and break the model, either numerically or analytically, introduce your own ideas on how individuals would be crossing it. It helps to kind of set the stage for where you would move forward with being able to kind of take this to the next level, either of applicability or at least to help tease out some of these nuances on best design practices, for example. Just a couple of
if you're interested in extending this one, I mean, to the group, like, I actually think it might be fun, a way to play with the MAIDS diagramming. If you look at the generative metagames GitHub repo, you'll see the example with the killer tree, but it's staged, and it's possible to have concurrent decision making. And so I think the natural extension of this is where there's a set of decisions about whether to drive down the road on one side and a set of decisions about whether to cross the road on the other, and that there's like an interaction effect between two different stakeholder groups by way of a coupling mechanism, which is the road and the crosswalk. So by extending it that way, we'll break down some of that like limitation that was encountered, not in this one, but the previous discussion. You end up starting to work around those limitations by looking at the way that these sort of blocks compose. And I'll drop a link in the channel with the some of that exploratory work, but it extended out of the collaborations with David Wolpert and all.
Nice, nice. Very good. And then just to wrap up, future work on our side, of course, it'd be great to implement an example at some point as a CAD 1.0 dynamical system, really leveraging the block point of view. And then something that is also on our plate, on my plate at least, is to describe the formalisms that connect GDS to CAD 1.0 through kind of specifying in one-to-one fashion the mathematical structure underlying things like the blocks and the spaces that CAD 1 is putting into place. So these are different directions for work, and otherwise, I hope it was of use. And again, we'll be trying to sort of repackage and repurpose these and other lectures and other outputs as they come about. So thanks very much. Questions or comments?
Could I see that slide with the matrix again?
Yeah.
Can I see the other slide with the matrix again? Can I see the next slide?
Yeah.
The next one? Oh no.
We've got this one, and then we've got this one.
Okay. Yeah.
Go ahead. Which one are you looking for?
A few forward from this.
Okay. So we've got that one, the M matrix itself. Got that little term from there.
Yeah. Okay. Remember that discussion we had 2 meetings ago about the first matrix?
Yeah.
Something about along the line, not that one, but the one before.
The one that was sort of crafted as a dummy. So before this actual, yeah, okay, I know which one you're talking about. Let me see if I can find that.
Go back. Yeah, you just had it. The first, it was. Okay, we're at the very beginning here. So I put the matrices. Sorry, now it's going to be very slow. But hold on.
So this is like a rehash. Now you get to see all three at once. That's an added bonus of the presentation.
Yeah.
But I'll get there. Let me move out very quickly to the presentation itself to go faster here. But you want the generic one, not the one for the problem, if I remember correctly.
Well, I saw all of them in this latest present. I mean, I'm seeing these matrices in this presentation. That's why I was going back.
This one? This is the one that was the test one, the one that we just sort of set up as a random idea as an example.
Okay, can you go back to the one that looks like this in the slide, the presentation you just had?
Yeah. So that is here.
Because I got this book in the mail yesterday, and I've been highlighting themes that I see in this presentation in the book that I just got.
Okay.
And it's called Data-Driven Science and Engineering.
Oh yeah, I know that. Yeah, in fact, we were just talking about that, I think, yesterday. With Zargham and Will.
I got the second edition, and I was looking at it yesterday, and I'm seeing a theme between this Markov process, and I don't know, I'm just trying to map it. Okay, because I remember we had a discussion about the last matrix, not this one, concerning that matrix was a reduction from a matrix of higher dimensions.
Right. And that's part of what we were describing was how are we going to be able to understand the different state space locations that we choose as the places that we desire to have reachable states occur. So one of the reductions is to say we only have 3 different locations, and so that gives us this 3x3 matrix environment. But the other way is to say that we have restrictions upon how individuals impact the probabilities. And so rather than have very, very large space movements or large decision-making that's being placed inside each of these little matrix entries, we're just saying there's a function of the things that we can observe if we were standing on the side of the street and just writing down notes and watching people cross.
Okay, and are the, okay, so within this context, is a generalized dynamic system model. Is it being represented as a Markov process?
In this example, yes. And it's only in this example that is crafted explicitly to take advantage of the notion of making a transition from having, for example, a traffic jam to flowing traffic, or from flowing traffic to an accident, and so on. So it's designed to kind of incorporate that intuition into a simple stylized representation.
We're not necessarily restricted to finite state machines the way that this example is. We've actually made a great deal of effort to ensure that our state spaces are effectively arbitrary topological spaces as codified by a type system. Basically, you can have an arbitrary object in compute, an arbitrarily computational object as part of your state, which is why CAD both legacy and 1.0 had what essentially key valued partitions and then types that could fit under that. So we could structure, you can think of that as structuring a space using dimensions where dimensions are typed. But we simplify to something like a finite state machine for the purposes of educational examples. A lot of the real systems that we work with for our clients have some pretty challenging state spaces that we actually do some of this work just to understand their structures even before overlaying any sort of incentives, just trying to get a sense of what the appropriate world model is for the purpose of evaluating any changes like in this crosswalk case, the world model involved the flow of traffic and at least the desire to cross the road, and the potential transition of of flow to traffic jam to accident. But like those concepts were kind of constructed to model the world. When the thing that you're building is software, a lot of the machinery is actually state transition in a very explicit sense. Like the actual state of the software is transition.
I'm trying to determine the utility of the reduction and why it is represented. It's being represented as a Markov process. And
this is a very simple example, like
simple.
from a
okay, because in the book, okay, I'm seeing all these themes that I've encountered, right? And I'm even seeing model reduction. I'm seeing a Markov chain as a neural network. I'm seeing a control feedback loop, and it's like
there's a reason why I recommended that book. It has a lot of shared principles and techniques that are and techniques that are explicitly useful and used by us. With the one caveat being that because we work on a special class of problems with smart contracts, a lot of the time, we have a much higher degree of fidelity with regards to the underlying system's laws of motion. So if you're working on a physical system, arguably, at best, you have a physics-based model representing how you believe it behaves and some parameters that you need to system ID from data. Whereas in a smart contracting setting, in fact, some of the explicit parameters of the plant, the laws of motion, are known. The exact laws of motion themselves might be known. We still don't know a lot of the behavior, which is why we end up with mixed methods between things that are like, we know this part works like this, and we believe this part works like that. We make strong separations. You won't see as much of that separation in the other literature because they don't have as much differentiation between the parts of the system with really strong, I literally know it works like this, and some subset of the state is directly measurable, like precisely observable. And so just being clear about what is and is not observable, what aspects of the plant are known for sure versus are estimated, goes a long way to breaking the problem up in GDS.
Well, I mean, remember that that lucid chart I shared with that was kind of like a control feedback loop representation of what I thought my role was?
I mean, I remember the chart, but you're welcome to describe it if you like.
No, I'm not going to. It's just like when I drew that, I'm just like, okay, I've been influenced, so I have to read this book now. You know what I'm saying?
Very nice.
It's good. Pretty much. It's like, okay, then if I've been influenced to that degree, then I might have some intuitive understanding of what's going on in the book. So I bought the book.
Yeah, that makes me think as well, it might not be a terrible idea for us to construct a sort of like a canonical textbook list or a canonical book list that we can maintain it over time. But, having some shared resources can go a real long way to coordinate, especially when we're working remotely and we're invoking all these concepts. That book in particular, the data-driven science and engineering one, is valuable. I shared a couple other ones from signal processing and numerical analysis, and then I've got like a nonlinear systems book. But I still have a stack of books that I'll break out when I need to look up a concept, because I haven't memorized how to do every technique. I know Jamsheed has a lot of great references as well, and it might be worth compiling a list of no more than 25. And I say 25 because we're working across a bunch of disciplines. It could easily be 3 to 5 per domain and still like add up really fast, as a way of sort of not saying everybody should go buy all those books, but more just like recognizing that having some shared references will help with facilitating communication. You can be like, oh, hey, I ended up pulling the technique from page whatever in textbook, whatever, but like with a realistic expectation that someone might actually have that book or have at least seen or read that material before.
Well, I have, I'm building my, go ahead.
I just wanted to interject very quickly just to give Chris just a chance to kind of quick comment in the last 5 minutes that we have on his question, if that's okay.
Yeah, it's fine with me. I think we were just sort of using the time because it is
no worries. Chris doesn't, he's gonna slack me on it. Sorry, go ahead, Josh.
Because, okay, so I figured if I mean, 25 books, 37 books, there is a book list. I posted it in the chat, but like, I'm trying to have a curriculum of 4 books, around 4 books. This is the one that I just mentioned is one of them. There are 2 others that there are, well, 5. There are 3 others that are related to, there are 3 others that are related to the type of engineering I'm doing now. The one I mentioned, this data-driven science and engineering, I think I'm trying to use it as a means of just understanding the context in which I am working, right? So I don't know, I kind of want to use CAD myself, if that makes sense.
Cool. I like your reference to Machiavelli. I'm curious as to how that fits into cats.
Reference to what?
Machiavelli. You've got Machiavelli, the prince, in your list. So.
Oh, I don't know where I got this list. I know I got it somewhere in Slack somewhere a long time ago.
That's right.
But yeah, there's this other thing I saw in the book. It was like reduced order models, like proper orthogonal decomposition in the SVD algorithm applied to partial differential equations. It's like dimensionality reduction within the context of this. And I was wondering if the reduction that we were talking about, where it was reduced to 2 in that matrix, was related to that.
Not directly. It is something that can be applied if you have a very complicated higher order system and you want to just tease out the regularities. Then doing a decomposition, a singular value decomposition, to be able to pull out just the salient features of it, which usually shows you from the matrix structure a partition of the space into usable subspaces, that can often reduce the problem. So tangentially, there's a little bit of a connection between thinking of the state as anywhere on the line and thinking of the state as flowing traffic, stop traffic, accident, as a means to which you can actually get a nice representation. More and more, I would say that the higher the dimension is, the innately higher dimension that you have, the more difficult it is to get those slices or facets that are low dimension. But you still need to do it, right? Otherwise, we can't really make any headway. So it's related in that respect, that you get some idea of the partition of the underlying state space from SVD. Its application to a differential equation is simply telling you, where is it that the trajectories themselves are going to be over time, conditional upon the fact that you can partition these particular reachable states or reachable subsets for that particular state transition. I don't know if that made sense.
Well, I endeavor for it to make more and more sense over time, because it's like, okay, I'm in a unique position where this stuff is interesting, and if I study it, I can somehow teach myself with help because I'm here.
Yeah, I mean, that's awesome. And that's would be kind of part and parcel of one of the desirables of the forum, really, is to be able to do that. And insofar as these materials can help, of course, that's half the battle. So, any questions or anything else that come up, just source them in Slack. Of course, we can come back to these in other presentations. But that's really, as we were talking about at the very beginning of today, getting this stuff out there and ensuring that everybody, at least within BlockScience, is on an equal footing on how they understand the abstractions, not in every detail, but at least the reasons why those exist, and then how they are applied to something like a reference implementation in CAD/CAD is, I think, really valuable.
Because I've worked on these things in different projects early on. I understood it, and I understood the process, but I'm trying to have a bigger picture. I'm trying to have a way bigger picture than what I have. It's gotten bigger over time, but yeah, this is the opportunity to do that. I'm going to take advantage of that.
Josh, I just opened that list too. I mean, that's very eclectic. I think I probably was responsible for some of it. I think there was like a crowdsourcing effort at one point for a list, and it's a little bit dated in the sense that there's lots of things not on it that I feel like I've come across in the last couple of years. So, one question is just whether or not, a co-curated reading list with some categorization and tags is something that we want. Then I think it might be fun to like just sort of unofficially maintain, the spreadsheet as database, as people can contribute things that they've found valuable. One thing I liked about it was that it does go from a pretty wide range of like I'll say philosophical or ideological extremes. You see things ranging from, Enlightenment, theory to sort of stuff like Rand to stuff like Ostrom, and I'd love to see. I don't think it was in there. Hirschman, Schumacher, like it, but it's still also relatively light. I don't think those are textbooks for the most part. That's all like more in the like. I think of them as being lighter. In terms of a textbook list, I'm thinking about things like your data-driven system, data-driven science and engineering. Like I have my nonlinear systems book literally open in front of me because I was popping it open to look for a reference for the topic I brought up about solving dynamical systems with and without driving functions. Like that's a pretty canonical concept that you can find definitely in a linear systems textbook. And I was actually looking for the comparable thing that might arise in the nonlinear systems canon. There's also, any number of books on a bunch of different topics, and I'm kind of finding myself concerned that the body of literature is so large that if we don't structure it a little bit, it's just not possible to find good references, right?
But even textbooks, okay, the distinction between textbooks versus non-textbooks. Textbooks, I believe you're referring to something that is a learning aid or a learning material.
I wouldn't distinguish them that way, actually. I think it's more that the writings that are more, I'll call them sort of like, maybe normative is the right word. It's like they take some assumptions, they might have an ideological basis. They're like, you read them, you think through them, you enrich your set of perspectives that you understand, but you don't necessarily want to adopt the things in the book. So like you might know about those things, understand that way of thinking, but what you're not doing is making a clone of the statements in your head. What you're doing is learning from the arguments that are laid out and like sort of taking into context some of when was the book written, like what was the cultural, political, technological day, because it ranges over centuries. I mean, I think Plato's Republic is in there. So like, to Jamsheed's point about Machiavelli, like you need to understand these things in their context versus like a textbook. A modern textbook is like, here is the reference for nonlinear systems. Those are very different relationships with books.
I mean, there's a difference between adopting an ideology and understanding it.
Yeah, for sure. I think that's my point. It's like wonderful to, I mean, like I've read a lot of things on that list, and I find it extremely helpful to have those mental models in my head. In fact, it's very valuable for the kind of work we do. But just I'm trying to separate the statements I was making before about, a book list of order 25 things. I'm actually talking about like more a reference base. So things like the data-driven science and engineering, or like my nonlinear systems textbook or my signal processing textbook. These are
at the same time, these other books like Jamsheed's phrase into hooks to hang your intuition on. They can be read side by side.
100%. Like, I'm no arguments. I am in fact not in any way saying that either is good or bad. I'm simply pointing out that they fulfill different functions in your like learning apparatus, right? You need to separate them a little bit because you need to, it's almost about like the difference between the mechanistic part of our models and the sort of more behavioral part of our models. Like even though they're very similar, they take the same form, book, the relationship you should have with them is different.
Yeah, it's different. And yeah, I got a little spooked when I saw Cat's Cradle.
Have you not read that? That is an amazing book. You should read it. It's Vonnegut. Nothing like developing the technology that ends the world.
Yeah, Ice Nine Kills.
Well, cool. I know we're over time, so I'll officially bring it to a close, I guess, since I'm emceeing, I guess. But great. It was awesome. Nice discussion afterwards. And thanks, everybody. So I'll get the slides as usual into the channel the next day or two. Ditto for the Jupyter Notebook. I'll try to comment that a bit more so people can kind of play with it. So thanks again.
Thanks, guys. And hey, Orion, I think it would be super helpful. We have to kind of gather requirements insofar as we figure out what the team wants and needs. But I have a suspicion that the first version of this may literally just be a Google sheet with 2 tabs, one for textbooks and one for more like, like more general reading. And like at worst, we might have some tags to say, hey, this is of this kind in the spreadsheet. And that would be a starting point. If people actually want to make use of that, then we can think about more than a spreadsheet at some point in the future.
Yeah, I think a spreadsheet seems totally suitable.
Yeah, but I actually think that it's almost more normative. It's like if we have it and people know that we have it and they find it a good way to share with each other the things that they've found helpful, and that yeah, I do actually want to keep the tabs separate for textbooks and for just sort of regular reading, because there's a lot of things that I've read that I don't actually agree with very much, but I still think people should read them.
Mm-hmm.
The spreadsheet needs to exist and it needs to be discoverable.
Yes,
That's the one.
it needs to be discoverable.